If quantum computing gets involved in AI, what are we looking at?
So we're talking about an extremely powerful alliance between software and hardware. The chatbots that are a revolution in software, and then quantum computers, which are a revolution in hardware, when they get together, watch out.
Michio Kaku, being a theoretical physicist and a futurist, often discusses the vast potential and the challenges associated with emerging technologies, including quantum computers.
Now, I'm a scientist. We like to think about things that are creative, new, innovative, things that'll change our perception of the world.
His concerns about quantum computers primarily revolve around their potential impacts on security, privacy, and the social fabric, rather than a fear of the technology itself. Now, how do these computers exactly work? Quantum computers bend the rules. Unlike regular computers, they use qubits that can be 0, 1, or both at once. This mind-blowing ability lets them tackle problems impossible for classical computers.
Quantum computers are powerful enough to survey the entire landscape and give reasonable rebuttals.
Building them is like engineering sci-fi. Qubits are coaxed from exotic materials in near absolute zero temperatures, but the hardware is just the start. Special instructions like quantum gates are needed to manipulate qubits and perform calculations. These delicate systems are prone to errors. Scientists use complex protocols to act like quantum mechanics ninjas, constantly fixing mistakes without disrupting the qubit state.
And just remember that where do correct ideas come from? Correct ideas come from interaction with incorrect ideas.
Keeping them stable requires extreme measures. Dilution refrigerators, essentially superpowered freezers, are used to minimize noise. It's like building a computer and sticking it in a giant vat of liquid helium. While the mind-bending potential of qubits existing in multiple states simultaneously promises to revolutionize problem-solving.
Quantum computers are the ultimate computers because they're computing on atoms, and they can do calculations that are far beyond anything that we can calculate with.
Keeping these machines' operational presence a unique challenge: extreme cold. Superconducting qubits, a common type, require temperatures near absolute zero, colder than the depths of space. Enter dilution refrigerators, the unsung heroes of quantum computing. These superpowered freezers constantly whir away, maintaining a frigid environment for the delicate qubits. The downside? They consume energy like a small country, upwards of tens of thousands of watts. But here's the surprising fact. While the calculations themselves might be energy efficient for specific tasks, the supporting infrastructure behind quantum computers comes with a hefty energy cost. Dilution refrigerators and the intricate electronics needed to control and read qubit states are real power guzzlers. So how exactly do these mind-bending qubits translate to mind-blowing speed? Here's where the true magic of quantum computing unfolds. Imagine having 1,000,000 coins spinning in the air, each able to land on heads or tails. A regular computer can only check each coin one by one, but a quantum computer can analyze all the possibilities simultaneously thanks to superposition. This parallel processing power lets them tackle problems in a way that would leave even the most powerful classical computers in the dust. But it's not just about raw power. Quantum computers also have special algorithms designed to exploit the unique properties of qubits. Take searching a massive unsorted database for a specific item. A classical computer would have to check each entry one by one, but a quantum algorithm could find it in a fraction of the time.
We have to get used to the idea that quantum computers introduces a whole new way of looking at reality.
This dramatic speed-up paves the way for tackling challenges in fields like medicine, materials science, and artificial intelligence, where complex simulations and calculations are currently bottlenecked by classical computing. Now, the realm of digital security is on the cusp of a significant transformation, courtesy of the advancements in quantum computing. This leap forward in computational capabilities brings into sharp relief the vulnerabilities inherent in our current cryptographic systems. Traditionally, the bedrock of digital security, public key cryptography, finds itself particularly exposed. This cryptographic method, which secures everything from our emails to financial transactions, relies on mathematical challenges such as the factoring of large prime numbers, and solving discrete logarithm problems. These tasks, though straightforward for computers to perform in one direction, are exceedingly difficult to reverse without the correct key, making them secure against attacks from classical computers. However, this security is predicated on the limitations of classical computing. Enter the world of quantum computing, where the rules of the game change entirely. Qubits, they can exist in multiple states simultaneously, allowing quantum computers to perform many calculations at once. This ability poses a direct threat to the foundation of public key cryptography. For instance, RSA encryption, which is reliant on the difficulty of factoring the product of two large prime numbers, could potentially be undone by a quantum computer in seconds or minutes, a task that would take a classical computer thousands of years.
Quantum computers allows us to calculate things that are way beyond our ability to calculate today.
The introduction of Shor's algorithm in 1994 was a pivotal moment, showcasing the potential of quantum computers to solve these heretofore intractable problems at speeds unfathomable to classical machines. This algorithm can efficiently factor large numbers and solve discrete logarithm problems, rendering encryption methods like RSA, Diffie-Hellman, and ECC vulnerable. The implications of this are profound, indicating a pressing need for new cryptographic standards impervious to quantum computing's capabilities. On the flip side of this looming threat is the emergence of quantum cryptography, offering a glimmer of hope in securing communications against the prowess of quantum computing. Quantum key distribution, or QKD for short, a novel approach in this field leverages the very principles of quantum mechanics that threaten current encryption methods to secure communication channels. QKD's security foundation is not computational complexity, but the physical properties of quantum particles. A standout feature of this method is its incorporation of the no-cloning theorem, which states it is impossible to exactly copy an unknown quantum state. This principle ensures that any attempt at eavesdropping can be detected, as interacting with a quantum system to measure it invariably alters its state, thus alerting the communicating parties to the security breach. As we delve deeper into the potential of quantum computing, it's impossible not to marvel at its revolutionary capabilities. This leap forward in computational power promises to unlock solutions to problems that have long remained out of reach for classical computers. Yet, as with any significant technological advancement, the introduction of quantum computing brings with it not just opportunities, but also substantial risks and challenges. These advancements suggest that the day when quantum computers can crack current encryption methods is not a distant future scenario, but an impending reality. However, the implications of this quantum leap extend beyond the technical challenges of upgrading encryption standards. They touch upon the very fabric of digital privacy. The strategy of harvesting data today in the hope of decrypting it tomorrow poses a unique and delayed threat to privacy. Information that is encrypted and considered secure now may, in the future, be laid bare, exposing individuals to a spectrum of risks from identity theft to financial fraud. Continuing our exploration into the quantum realm, let's pivot to another area where its impact is both promising and profoundly unsettling: the financial markets. The advent of quantum computing is set to usher in a new era of opportunities and risks, fundamentally altering the landscape of financial analysis, trading, and the very fabric of digital currencies. Cryptocurrencies, for instance, stand on the front line of this quantum revolution, renowned for their security, which is underpinned by complex cryptographic algorithms like SHA-256 for Bitcoin and ECDSA for Ethereum. These digital currencies rely on the computational impracticality of breaking these cryptographic codes. However, the theoretical prowess of quantum computing threatens to dismantle these cryptographic defenses, opening the door to potential double spending attacks or the unauthorized creation of coins. This isn't just a minor glitch in the system. It's a foundational threat that could undermine the integrity of blockchain technology itself, allowing malicious actors to alter transaction histories or abscond with funds. The mere hint of vulnerability to quantum attacks could shake the very confidence that has buoyed cryptocurrencies, leading to market volatility, plummeting values, and a re-evaluation of digital currencies as secure, decentralized financial instruments. The ripple effects of such a scenario are hard to overstate, potentially reshaping the landscape of digital finance. But the influence of quantum computing extends beyond the realm of cryptocurrencies, promising to redefine financial modeling and prediction. With the ability to process and analyze complex financial systems at speeds and depths unfathomable to classical computers, quantum algorithms could offer unparalleled insights into market trends, risk factors, portfolio optimization, and arbitrage opportunities. This quantum leap in analytical capabilities could transform how we understand and interact with financial markets. However, this quantum advantage doesn't come without its own set of challenges, particularly in terms of market fairness. Imagine a world where a select few have access to quantum computing resources, enabling them to make informed trades based on predictions far ahead of the market curve. Such a scenario would not only disrupt market dynamics, but also raise significant regulatory and ethical questions. The potential for an unfair competitive edge necessitates a rethinking of financial regulations to ensure a level playing field, where quantum-enhanced insights don't undermine the integrity of the markets.